want to do quickly. Yeah, so let's start. Oh, also, I was actually seeing, let's say you want to check if a linked list is a palindrome, right? So we have one, two, two, one. This is a palindrome, right? Because it contains one, two, two, one. So the palindrome is a number. When you read from the front and remove from the back, they're like the same thing. So one. So as you can see here, we have one, right? One, 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 two, two, right? And one way you can actually do it is, and we've also solved in your practice problems, you've also learned how to reverse a linked list, right? So one approach to solving this question is to, just find the middle. And we've also learned, so let me show you like how you can apply all the things we've learned. So we've learned how to find the middle node of a linked list, right? I hope we have, right? How to find the middle node. We've also learned how to reverse a linked list, right? And all these things are things we have discussed in class, like class, like 2 times, right? So let's see something here. How about we find the middle node, right? Here, where the middle is like the second node, because this is an even length list. So here, let me find the middle node, right? So we get to 1. So we apply the middle node algorithm we already know. Then we apply the reverse linked list algorithm we also know. Then you reverse this. The moment you reverse this, what does it become? It becomes 1, 2, right? So this is 1. This is the first half, 1, 2. And this is the second half, 1, 2, right? And you know that you can simply unlink this by just setting this one's next to be none, but this one's next to also none, right? And now you can just start with one pointer here, pointer 1, P1, and pointer 2, P2, and just move them. Compare this to this. Are they the same? Yes. Then you move each of them 1, 1, right? Are they the same? Yes. And then you are done, right? So that's what I'm talking about. You learn the foundational ones we give you, like you learn how to reverse a linked list. You learn how to, find the middle. And when you get a question like this, all you have to do is just merge those two techniques, those two algorithms, and you solve one. In an interview, when an interviewer gave you this, they could be like, so how about if we, we reverse one half of the linked list, right? A good interviewer will probably give you that thing. And you don't expect them to now teach you how to reverse a linked list, right? They've given the clue. How about if you reverse one half of the linked list? So you can be like, how do I reverse one half, right? That's not helpful. So please do the problems we give well. They will lay very good foundations for you. Okay. And the other one was also linked list cycle. That almost got me sad because Floyd has got more fans in like this place than he's probably got in his whole life. Okay, so you're like, if you have something like this, you can just start 2 pointers, like fast and slow. Move fast 2, move slow 1. Like this is something we've discussed like forever, right? Move fast 2, fast comes here, like move slow 1, and like they'll merge, right? So please take them seriously. Let's go to what I wanted to do today, BST. Basically, let's just do trees in general. We don't have time, honestly, so we just well next week we'll use the first half to complete trees, and then we do the problems session. Anyone has any questions? Does anyone have any questions? Okay, let's just talk about trees. So we were basically talking about node-based data structures, right? And we said node-based data structures simply, have, so let's assume this is a node. A node is simply, just a circular object, right? I mean, just illustration purposes. Then it contains something called, the data. That's the actual value you want to store. And it contains some extra information, right? And usually this extra information are just, pointers. They are pointers, or they contain, addresses to other nodes, right? Or addresses of other nodes, right? So like if we have this like this, so like we can actually use the linked list. Like, so you have the linked list like this, the value can be here, right? And that's, that pointer for a linked list, that pointer is what we call the next pointer, right? The next pointer simply points to the address of this other node, right, in memory. So that's what node-based data structures are. They contain the value, the actual data you want to store, and some extra data that is usually pointers to other other nodes in memory. So today we talk about the tree, which is also a node-based data structure. And trees are just like trees we see in our homes and in our farms. So this is actually a tree. And yeah, so for a tree, let's cover some properties of a tree. A tree has a topmost node that we call the roots here, and it also has children, right? So this is how we call the children, right? Now a tree can have many children, right? It can have like 1 child, 2 children, like 1 billion children. It doesn't matter, right? So you can have a tree like this, right? It can have as many children as possible, right? This is actually a tree, right? Now a tree with at most 2 children is what we call the binary tree, right? And that's usually what the focus is on, a binary tree. That's a tree that has at most 2 children, which means that for every node, right? For every node, that node can have 0 child, right? That's like it has no child, or it can have 1 child, right? Or you can have 2 children, right? So this condition should be true for every single node, right? So this is node 1, this is node 2, node 3. Node 1 has 2 children, node 2 has, no child, node 3 has no child. So this is actually a binary tree, right? And the condition must hold for every single node. So to reiterate, a binary tree is a tree in which every node has at most 2 children, right? This is one of the next important thing. The next thing you also want to keep in mind that so these things, right, actually just show a relationship. These things you see here just show a relationship, right? So this simply means that 2 is a child of 1. So the relationship shown here, we usually call them edges. Like these lines are usually called edges. So like this is called a node, this is called an edge. But you can just keep that one at the back of your mind now. So this thing just it shows a relationship, right? That's a child relationship, right? So if it comes down, right, if it comes down like this, right, it can also go up like this. I just want to show you something interesting here. So as you can see, that bar you see there does not have any pointers. This is what I want to mean. It is not like this, right? Neither is it like this, right? Instead, it is like this. It has no pointers here. And because we call it undirected, right? Undirected, which means that the relationship goes in both ways, right? The relation goes in both ways. So here we can say 1 is the parent of 3, and 3 is the child of 1, right? So trees are undirected, right? The edges in the tree are undirected. Please keep that in mind. This will become particularly important when you do graphs, because we define trees as undirected graphs, right? And those have no cycles. Yeah, so let's keep that in mind also. Okay, now let's go to next set of cool stuff. So let's just define a few terms. So there's something called, the height of a tree, right? And there's something called the depth of a tree. Depth, how we spell it? Doesn't look nice. Okay, then there's something also called, a balanced tree, right? Balanced tree. These are just some terms I think are good to know. So let's talk about a balanced tree first. So let's take a tree here like this. Let's assume this is a tree, and this is also a tree. Right, now this first tree, right? Okay, let's just actually add another one. Okay, so this first tree you see here is actually, this is an unbalanced tree, right? This is an unbalanced tree. This is a balanced tree, right? I should have actually asked this as a quiz, but we don't have much time. And this is also a balanced tree. So let's see what a balanced tree is. So when you talk about a balanced tree, it means that at each level, right, the number of left nodes, right, or let me just put it this way, that at each level, right, the height, and can you even see this? The height of the nodes in one subtree is at most greater than the other. I'll explain this, so don't worry, than the other. Okay, so let's see what we mean by this. What we simply mean is that if we take this tree here, right, if we take this nice tree here, right, and we take, the left subtree, that is this is the left subtree, right? So let's just take even just this left. Let's say this is the node, this is the left subtree, right? Everything here, right? The number of nodes here is just 1, right? The number of nodes here is just 1. Then if you go to the right part too, the number of nodes here too is just 1, right? So this is 1, this is 1. It is a balanced tree, right? Assuming this was 3 and this was 1, right? If you subtract 3 from 1, it's 2. That is an unbalanced tree. So for a balanced tree, when you calculate, the height here and the height here, the difference can be at most 1. That's what we call a balanced tree. If we come to this part, right, let's take this one. If we come to this one, if we look here, right, if you look here, we have, just one node here. So here we can say, okay, that's height of 1. There's only one node here. If we go to the, if we go to the other part, if we come here, we have like 1 here, then we have 2 here. So at this part, it is 2, right? So this is still balanced because the difference is 1, right? But let's look at an unbalanced tree. An unbalanced tree, this is indeed 1. We can see here, right? This is the left subtree. But then we come here, we have 1, 2, 3. That is more than 1. So this is what we call an unbalanced tree. Does that make sense? So for an unbalanced tree, if you check the height of the left subtree, check the height of the right subtree, right? For an unbalanced tree, they differ by more than 1. But for a balanced tree, the difference is at most 1. Does that make sense to everyone? Does it make sense? It's going to be in next week's practice problems. Does this make sense?
Yes.
Okay, good. Now let's go to the next thing. And actually, algorithms actually find this. So I know you people remember we did recursion last week, right? We did recursion last week. So let's say we can actually write code to actually, compute this. So let's just see. So let's say we want to say find height, right? So for now, let's define height to be the number of nodes in a subtree. So assuming we have this thing here, right? I'm going to show you another interesting application of recursion, the recursion technique that we discussed last week. That to write a recursive function, what do? You assume the function works, right? Then you just call it on the subproblems. So let's assume here you want to write a function. Let's just call it count nodes. And what our function does is that it counts the number of nodes in a tree, right? Counts nodes. So let's just say we pass the root node. So just like a linked list, for a tree, you only have access to this one, right? It is the only thing you have access to. So let's just pass it here as roots like this. So as we discussed, you can just write our base case, right? So base case is if it's none, right? If it's none, or if like if there's no whatever, we can just return 0, right? That's like if the tree is an empty tree, right? Then what can we do? We assume our function. So this is a function we are writing, right? Count nodes. So what do? We assume the function works and has been implemented for us. Do we all remember that technique, that assume the function works and it has been implemented for you? And with that assumption, what we can do is that we know that this whole thing is a tree. Please follow me carefully. We know this whole thing is a tree, right? This whole thing is a tree. But we also know that this one is also a tree, right? Because it's just the same structure. It has a root. Like if I just consider this part, it has a root, it has, edges and everything, right? Technically we call it a subtree, but a subtree is still a tree. And it's the same thing here, right? What do you call it? A node is also a tree on its own, right? A node itself is also a tree. So with this understanding, that means that if I can assume that my function works, right, count nodes works, and I call count nodes on the left subtree, I am believing that it will return to me the right answer. Does everyone agree? Does everyone get what I'm trying to say here? That by assuming that count nodes work, if I call count nodes on the left subtree, I should get the right answer.
Yeah, but I'm confused. Why are we returning 0 if we find the root?
So actually it's if not root. Oh, sorry. This is if not.
Okay.
Right. That's like if the tree is empty, right? Thanks for that. Yeah.
Okay.
Good. So that's basically our structure, right? The structure. Okay, let's now write the definition of a node. So assuming that a node, right? A node here. So let's just write this is the init, has a value here. It has a left and it has a right, right? A left simply means, so as we said, this is the data you want to keep for a node. These are the extra information, the pointers. So the left is this left. The right is simply this right, right? Good. So with that assumption, everyone believing, that means that if I call count nodes on roots.left, we are going to believe that it's going to return to us the right answer. That is the number of nodes in the left subtree, right? In that same vein, we are going to believe that if we call count nodes on the right subtree, we're going to believe that it is indeed going to return to us the total number of nodes on this right subtree, right? Does this make sense? So this is our recursive case. So our base case was here, and this is a recursive case where we call the recursive function. Again, this is our recursive case. Does this make sense so far? Does this make sense to everyone? Before we go on, does this make sense?
Yes.
Yeah. Okay. Now the last thing we said we do is our combination step, right? Combination step is okay. So we are believing that the function works, right? So we know that this whole part is going to return to us 3. This whole part is going to return to us 2, right? But then what is the actual answer? What is the number of nodes in this tree? What is the total number of nodes? Anyone? How many nodes are in this tree?
3 plus 2 plus 1.
Good. 6, right? So that means we're simply going to do return 1 plus left plus right, right? And we know that this 1 here, it's simply counting this root node, right? So we counted the number of nodes here, then 1, and that 1, it's simply for this one. And this is indeed all the code, right? To count nodes in a tree. Just assume your function works, count the number of nodes on the left tree, count the number of nodes on the right tree, then, on and off you go. And that is all you need. So this is all you need to write a function to count the number of nodes in a tree. So you see, we're actually building upon the things we've learned. Last week we learned how to recursion, how to write recursive functions, and we just adapted that same technique to implement this. Does this make sense to everyone? Does this make sense to everyone? Before we go on to the next thing?
Yes.
The next thing we can also do is It's actually been in the practice problem, but let me just touch on it briefly. So we just discussed what a balanced tree is. And we said that for a balanced tree, right, their heights, do not differ by more than one, right? So we can actually use the same technique, right? We can be like, okay, let me assume that I have a function called height, get height, right? And what get height does is it simply gets me the height of a tree. So someone will be like, okay, then assuming my function works, I can use that same technique. I'll call get height on this one, right? So I'll call get height on the left subtree. Then I'll call get height, right? Get height on the right subtree, right? On here, right? I'll call here and I'll call here. Then what do? Then I'll check if, right? So let's just call this L, I'll call this R. Then I can just, subtract. But here we can use the absolute value, right? If the absolute value of left minus right, right? Because like, you don't know which one is going to be bigger and everything, right? So if the absolute value is greater than 1, right? That means that one of them actually, outweighs the other by 1. So you can be like, okay, this is not balanced, right? This is not balanced. And on and off you go. So it will actually be in next week's practice, and then we go from there. Okay. So does the whole concept of binary tree make sense? If we go to binary search trees, we'll talk about the traversals and other. Yeah.
The question was in last week's problem. This question.
Oh yeah, but yeah, we didn't ask.
You've already given it to us.
Oh yeah, exactly. But we also add it again because last week, because we didn't do trees, we were like, people can skip it, right? So we just add it again.
Oh, okay.
Yeah. Now let's go to binary search trees. So we are basically explaining the concept now. Next 2 weeks, we will then go deeper into the algorithms and other implementations. Yeah. So let's look at BSTs. So BSTs are also binary trees. So it's a binary tree. Each node has at most 2 children, but with an invariant. So what are invariants? So invariants are simply conditions that hold true at the start and at the end, of a block of code. So this is what I want to mean. So there's something called, let's say something called a loop invariant. Let's explain a loop invariant first. These are like computer science concepts, which are really good to know. So loop invariants. So let's say that you have while fast, right? While fast and fast.next, right? While fast and fast.next, right? Then you execute something and then the loop ends, right? So the invariant is simply that to enter this while loop and everything, to enter this while loop, this condition must be satisfied, right? Like this condition must be satisfied. So that's an invariant. It's not going to change, right? Now, in the execution, the invariant may be broken, but at the end, it's still going to be restored. You don't even think about that. Let's just skip this. Let's just go to the invariant. Okay. So what is a binary search tree? It's simply a normal binary tree, right? With some, I don't want to say invariants, but with some extra things. What are the extra things? For every node, these are the extra things. I must know. For every node here, right? Each node in this left subtree, each node in left subtree must be less than it. And each node in right subtree must be greater than it. That's the simple invariant, right? So that's like every node in this left subtree must be less than its value, right? That value of every node must be less than that current node's value. And every node in its right subtree, right? Its value should be greater than it. That's a lot of English words. But let's just give an example. So 4, 2, 5, 6, 9. Is this a binary search tree? Anyone? Is this a binary search tree? Is this a binary search tree? Anyone can say yes or no. Is it?
Yes.
Okay, yes, it is, right? Because if I take 4, now it says every node in its left subtree must have value less than it, right? So this is a left subtree here. So this is the node here, 2, and 2 is indeed less than 4. Then we come to its right subtree, right? Every node in its right subtree, right? So here 5 is indeed greater than 4, 6 is greater than 4, and 6 is also greater than 5. 9 is greater than 5, right? The mistake people do is that sometimes they forget that, like, they just compare the node to its children, right? They don't consider the down ones. That would be wrong, right? So let me give you an example of what I mean by that. Let's assume you have 12, right? And then you have 9, and then you have like 10, right? Then you have like 14. Let's make this 110. You have like 14, right? And then you have like 200, right? And then you have like 7, then you have 17. Is this a binary search tree? Is this a binary search tree?
No. No.
Okay, can you tell me where something is violated? Can anyone tell me where something is violated?
The 14.
Good. So 14, right? So wait, why is the 14 violated? This is 14, right? Why is 14 violating something?
Because it's smaller than the 110.
And yeah, and that is true, right? Because so if we let's take the first node 12. So let's see how we can. There's also another question you have that we call validate binary search tree. And that is what we are discussing literally right now, right? So it's the concept, then you translate it into code. So let's take the first node 12, right? So this is how you test it. So you take 12, you're like, let's look at 12 children, 9 and 11. 9 and 1, 10, right? This is correct, right? Because take 12, go to the left, 9. 9 is indeed less than 12, right? 110 is indeed greater than 12, which is true, which is perfect, right? Then let's take 9, right? Then let's take 9's children. Then we take 7. Is 7 less than 9? Yes. Then go up again. It's 7 less than 12. That is also true, right? So for 12, each node, like here on this path, are indeed less than it, as we need, right? Then let's take 9 again. Let's take 9's, 9's right. That is 17. 17 is indeed bigger than 9, which is true. We said every node to your right should be bigger than you, right? But 17 is not less than 12. So that makes sense, right? So the what do you call invariance is breaking. Does this make sense to everyone? Does this make sense? That this whole tree is to the left of 12. This whole tree you see here, right? Like this tree here. Let's use a different color. Like this whole tree here is to the left of 12, right? This whole tree is to the left of 12. That means that each of these nodes should have values that are less than 12, but 17 does not have, right? 17 breaks it. So that breaks it, right? So one of the problems you do is to be called validate binary search tree. And this is simply the logic you have to implement, right? It's actually a very relatively simpler one. Call it and let's call it and right, then compare, just compare the values and then you are done. Okay, now let's go to why binary search trees. What makes them so cool? So some of you remember about last month, we discovered what we call the binary search algorithm, right? And we actually, use that same thing here, right? So the binary search tree, because of invariance, it actually has an order, right? Like the tree is structured in a specific order, right? It has this specific, beautiful order. So let's see something here. Let's assume you want to search for, let's say 6. Let's build this thing a bit more, right? Okay. Now let's assume you're searching for the number 6 in this binary search tree, right? So you only have access to the root. So you come here like, hey, are you 6? No, right? So do we go left or do we go right? Or do we go to other parts? Anyone, we're looking for 6. Where do you think we should go? Left or right? We are looking for 6.
Right.
We go right. Why do we go right? Because we can compare 6 to 4 and we're like 6, you are bigger than 4. And we know that all values that are bigger than 4 are to its right. So we can, discard this whole part. We can ignore everything here. Everything here can be ignored, right? Then we can simply come here, right? That is how binary search works. Binary search, like those of you remember, I hope everyone remembers, when you find the middle, you make a decision. Should I go left or should I go right? And you just compare, hey, are you bigger or smaller? Then you can discard, one whole portion. That is the same thing that is going on here, right? So we would just, we'd now come here. So we'd have come here and be like, hey, 5, are you 6? You're like, no, I'm not 6. Then you make the decision. What do you call it? So you make the decision again. Oops, this tree is actually also buggy. Can we tell this tree is buggy? Can someone tell me there's an issue with this tree? Is that an issue with this tree? Is that an issue with this tree?
Yeah.
What's the issue?
Yes.
What's the issue?
The numbers less than 5 should be to the left, but
Exactly.
6 is
6 exactly.
greater than 5, but it's to the left. So
yeah. So let's make this 15. Let's make this 6 and let's make this 19, right? So when you come here, you're like, hey, 15, are you 6? No, but I'm bigger than 6, so go to my left, right? So you'd have come here, then indeed you find 6, right? So searching in a binary search tree, it's n log n, right? That's searching in a binary search tree. Not just searching, insertion and everything also. Last caveat I'm saying, but this is not always the case. This is not always the case. It is only the case if your binary search tree is balanced. That's why we introduce balance at first. It's balanced, right? Now, let me show you why I'm saying that. That's the last thing that we are done. And it's actually something very important to know because when you go to when you do red black trees and other things, you actually come across these things. Let's take
I'm a bit confused.
Okay,
Isn't the search log n instead?
Oh, what did I say? Sorry, it's log n. My brain. Okay, it's log n, not n log n. Thanks for that. Yeah, but I'm going to show you it's not always log n. So those of you log n simply means that at some point you discard half of the input space. So if there were 10 elements, the first time you come through is 10. The next time you come through, you're only searching, out of 5, right? You cut across, how. Hopefully, maybe next month we will take time to really explain time complexities. But you're saying that is not always the case. You can be given a binary search tree and still do linear, right? So linear is worse, right? Linear is worse than log n. We always want to, log n, right? We open our mouth to go and solve log n. That's the one we want, right? But we are saying this is not always the case. In binary search trees, there are sometimes you can still get linear time, you can still get this thing you hate. And why is that the case? If the tree is unbalanced, right? So let me tell you what I mean. So tell me if this is a binary search tree or not. Oh, what am I doing here? Is this a binary search tree?
Yes.
Does everyone agree this is a binary search tree? These are like the right children, like their left ones are none, 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 none. Is it a binary search tree?
Yeah.
Yeah, we all agree, right? Now let's assume we are looking for 6, right? Let's assume we are looking for 6. Now you can see we will search everything, and that is O of n, right? This is perfectly O of n, right? Is this tree balanced or unbalanced?
Unbalanced.
It's unbalanced, right? So how can we do? So what we do is that if the tree is unbalanced like this, you don't get your O of log n, or you get O of n, right? That is the importance of a balanced tree. So what you have to do, you have to actually break down this tree and then balance it. And there are many ways you can actually balance this tree. One we can do is that we can actually put a 5 here, then we can put the 4 here, then maybe put the 7 here, then the 4 here, we can put 2 here, then we can put no, that would be wrong. And actually, the algorithms to actually, when you get time, look at red black trees and AVL trees also. So actually, you can go and do this one later. So yeah, so you get that O of log n if your tree is balanced. If it's in the worst case like this, you don't get this. So that's actually question I get in an interview. That is the time complexity of searching in a binary search tree always log n? Can be like no. When the tree is like this, is skewed like this, or balanced tree like this, you can actually get worst case O of n time complexity. So I'll actually be ending this here, and God willing next Sunday we'll go through we'll finish up on trees and binary search trees, and then we'll use the 70% of the time to go into breakout rooms and solve problems. But please, this week we are not giving you new problems. Just complete the questions we have released so far. Spend time on them, solve them, try to understand the solutions. Try to just make time for them, because those of you who want to get something, I mean, in this, we're in May 7th. Internships, for the summer usually starts in May, June, right? And then companies start recruiting in August, then September. Then once you push in your application, I usually apply in September, then they'll start getting back to you in September, October, and then you have to interview and on you go. You don't have time. And some of you will even be in school then. So you can't tell me you're procrastinating and then you do the grinding when you're, it's just going to be a whole bunch of something, right? But if you learn the things now, get the foundational concepts now, when school starts or the company starts reaching out to you, you can just revise, right? Like me, I just, sometimes I don't even know the solution. I put the question somewhere, I learn the solution. Then later, I try to code everything on myself. I get stuck, I revise and everything, right? So please don't procrastinate. Don't. Try to learn as much as you can now. God willing, in 2-3 months, you come back to all these things and revise every single one of them. But if you don't learn them now, when we come back on next 2-3 months, everything's going to look so new to you, right? I just showed you how many of the things we're doing is just repetition. Like this one, right? It's just repetition of reverse and find the middle and many others. So please, we are begging you, try to invest time in this. Take it seriously. Please take it seriously for our own good. All right. We are done. I hope I recorded this thing. I'm not sure. Okay, looks like I did. Okay, so if anyone has nothing, we are actually done.
I wanted to ask you something.
Yeah.
It's about this tree you were solving, right?
Yeah.
So if I could share my screen, I wanted to show you.
Yeah, you can share your screen. I think you can share your screen. Yeah.
Okay, thanks. Okay. So you see here, after right? So yeah, after I'm done creating the tree here, right?
Yeah.
Yeah, and you see, when I try to assign the values, you have to like
Mhm.
put them in the like have to call the class before you give them the values. So I can't be like root is equal to 1, root dot left is equal to 2. I have to implement it as root is equal to tree node. Then I have to before I
Oh,
can assign it. If I try that, I get this error. Int object has no attributes left.
yeah. So what you're doing now is go to your line 13, line 19, I mean line 19.
Line 19.
Yeah. So that is what you have there as else. So you're checking its same tree, right? So the error is being triggered from your its same tree.
Oh no, this code works, right? This code works. There's no error. My question is, why is it that when I'm assigning values to the left and the right children of the tree, I have to put those like the values you see here when I'm assigning 2 to the left of the root? I have to put that 2 inside the tree node before I can assign it.
Yeah.
Why can't I just do root.left is equal to 2?
2. Okay. I get you now. Okay, let me share my screen and explain that to you. Okay, I thought you wanted help debugging the error in your thing, but that wasn't the thing. Okay,
No.
let me show you.
Correct. Okay.
Let me show you. That's actually a very good question. So your folks can stay around and just watch why. Yeah, that is because trees are node-based data structures. But let me show you. Wait, my thing is loading and my thing is loading. Okay. Give it a few. Okay, but as it loads, let me just talk it. So trees are node-based. Okay, good. We have it here. Okay, good. So let's see why. So we want to construct a tree, right? So we want to construct a tree containing 2, 3, 4, 5, right? And as we explained the last time, assume this is your computer memory, right? And like how we did linked list, same thing with trees, right? So you want to create, want to store 2, 3, 4, 5. If you're using an array, right? If you're using an array, you could have simply, found some contiguous space, right? Like this, and put 2, 3, 4, 5 in, right? But you're like, maybe we don't want to use a contiguous structure. We want to be able to scatter our information in our memory, right? Someone's like, oh, I can use linked list, right? Where I have like 2, 3, 4, right? Then 5, right? So 2, 3, 4, 5, right? And maybe this is none, right? So a linked list would be like put 2 here, put 3 here, put 4 here, put 5 here, right? And all you need is just the links, right? This is how a linked list works, right? Right?
Yeah.
This is going to work perfectly, right? But know that for this one, like for this thing we just did, each thing right here, right? Each thing here is a node. It contains both the value that 2 you're seeing here, right? And a pointer, right?
Yeah.
And that pointer is simply what is pointing to this box also here, right? And trees are the same thing, right? Trees are also doing the same thing. If I do 2, 3, 4, right? It's like 2, 3, 4, right? Then this has a pointer here and this has a pointer here, right? It's the same thing. Now, the reason why you can do, now let's assume that you create a node. So let's just call it node 1. Then let's say you create a node of 1. So the moment you do this, right? The moment you do this, what you have done, that you have gone into memory and you have created one like this, right? This is what you have done, right? And ideally, if you're doing 3, that's like, let's even make it more explicit. So let's say the first argument is the value. The next argument is the left, what the left pointer is. Then the next one is the right. Let's assume this is what you have here, right? So when you do node value, so let's say we create a value of 1, and let's say we don't know the left yet, so we can put none here, and also put none here, right? So it's just going to put 1 in memory like this. Then you create node 2, right? And node 2 is, kind of like the same thing, right? Like node 2 is kind of like the same thing here, except now this is, let's say 4, right? This is 4 here. This is 4, like this. And now you want to link them together, right? Like you want to connect, maybe you want something like, you want node 1, then you want like node 2 here, right? Maybe you want something like this. If you want something like this, what you do is that, look at the trick here. So the thing is, what you do is that this node 2, right? You're going to, it's somewhere in memory, right? Like maybe it's this 4. It is somewhere in memory, right? So you have to put its address, right? You have to put its address as the value for the left in node 1.
For the next in node 1.
Yeah. So that's actually what you're doing. So we said these pointers actually save addresses to the next one. So if you want to establish this connection, what you do is that, okay, get to node 2. Where is node 2? This is node 2. That is why it is in memory, right? This is like a memory, like this memory. so just some house inside your computer, right? Then you're like, okay, take the memory, right? Where this 2 is living, right? Here, oops, what did I just do? Right, take this guy here, right? Take its memory. So let's assume that the memory is ID4. Let's assume that's how in memory, let's say information live in a house is called ID. So this guy lives in an address ID4.
Yeah.
What you do is that you put that ID4 here, right? So how do you do that? You just do node 1.left. So when you do node 1.left is equal to N2, this is actually what happens. It just takes ID4, right? It takes ID4 and then just puts it here. And this is actually very clear when you do it in the Python tutor we showed, right? But you see, programming languages don't want you to bother with memory, don't want you to bother with all those things. So they are like, just do this. When you do this, this is actually what happens under the hood. It gets the address of N2, right? That is, this node here. Then it will put that address, right, as a value for the left, right? Of N1. That's what is going on there. So this is a value, the data you want to store, but these kind of store addresses, right? They store addresses, left, just like the linked list. Next was just an address. So that is why. So 2, the number 2 is not an address, right? If you do N1.left,
it's
equal to 2.
It's just an integer.
So just a primitive type, right? And the last thing also is that you can see that you can follow the addresses to a node, right? If you follow the address, you come to a node, right? You come to a node. And from that node, right, you can then follow another link, right?
Yeah.
Right. But if you go to 2, assume you did N1 is equal to, the number 2, there's no links to 2, right? There's no links to 2. So that's why it was telling you that 2 has no attributes left and right, right? Because 2 is just a number and it has none of those.
Yeah.
So that's basically what it is. I hope I did.
All right. Thanks. I get it.
Yeah. Anyone has any questions? If anything, you can just send me a DM on Slack. I'm relatively faster to reply. And then we talk about but please do want to spend time on the questions. You can even save the videos on YouTube offline so you can watch them later. But please make time. Okay. Okay, I'm ending the meeting. If you want one-on-one to discuss as you go through these problems well, please you can just send me a DM. Also over the summer, when we're on break and everything, we'll actually have days where just a random thing where people will be online, like on Zoom solving questions, and you can join and we will have sessions to explain questions. But please try your best. Let's try our best. Okay, that's it for today. See everyone later. Bye. Wow, no bye.
Bye.
Good. Bye.
Bye.